We're just hitting 4 p.m. EDT here, so we will get started in just a second. I have a poll up, and we had 91% participation. So let me end and share the results for a quick discussion. You can see in the future, what do you see your conference workshop attendance? You only get to pick one, and very few picked increasing more because they need to get out. Though we all feel that at some point, I'm sure. Some remaining less as I get more done with less traveling, going back to normal, but the majority, or the highest winner is engaging in online hybrid with options as it improves. And I think the technology is advanced now that is now easier to conduct. I remember sitting in some of these meetings several years ago and hearing a disembodied voice over a loudspeaker. And I think that's becoming more and more possible to get done in an efficient manner. So online becomes a better option for folks, whereas it was a little more difficult before. So with that, we will stop sharing. Thank you all for participating. It's important to understand these items as we go forward. Our next session is on very specifically in a new session for us in forest monitoring. Soil monitoring in forests is not common, but there are certain locations with a history, and it's becoming more important as we move forward as one of the obvious locations where we need increased monitoring, and remote sensing tends to be a challenge in these areas. And modeling is not quite addressing the needs yet. It's the untapped frontier, as we may say. So our first presentation is by Elisa Senga at the Aspen Global Change Institute. And she's thankfully given us a variety, a new method of showing her presentation. I hope I took a little preview myself and found it quite interesting. So let me just get it shared. And
Hi, I'm Elisa Senga from the Aspen Global Change Institute, and I'm here today to give you a quick introduction to the Roaring Fork Observation Network, or IRON, which is our long-term research network here in the Roaring Fork Valley. Before I begin, I wanted to say a few brief words about AGCI itself. We are a nonprofit committed to advancing global change science and solutions. And throughout that really broad scope of work, we have kind of three unifying themes within the work we do. One is that we try really hard to be interdisciplinary in approach. The next is that we really try to have some sort of partnership or collaborative approach to the work we do. These are really gnarly problems we're working on. We feel like we need a really great diversity of minds to help us address problems like that. And then finally, we try to make sure that the work we're doing fills a need or a gap that isn't already being met in either the scientific understanding of or even the data itself for understanding global change. So the project I'm here to talk to you guys about today actually really exemplifies all those three qualities that I mentioned. So the IRON, our long-term observation network, is something that is interdisciplinary in nature. We're looking at ecology, we're looking at hydrology, we're looking at the interplay between the atmosphere and the soil and the streams. So we have a pretty broad approach to this work. Next, it is collaborative. This project would not have been possible without our partners. The vast majority of our funding for this project so far has actually come from local funders. And so it's really important to us as we do this work that we're constantly thinking about how is this data going to be applicable to our partners. And then finally, in terms of a data gap, as I probably don't need to say to this group, soil moisture is something that we don't have a whole lot of in situ data on. And so that's where we really saw a need in better understanding the water cycle and the interplay between what happens when our temperatures warm, what will that mean for our streams and rivers. So this station today that I'm going to show you is Sky Mountain. It's our oldest station. This network started in 2012. Today, the network has grown to be 10 stations wide, and it runs from the top of Independence Pass at 12,080 feet, all the way down to near Glenwood Springs, which has the confluence of the Colorado River, at 6,200 feet in elevation. And speaking of the Colorado River, I want to orient you about this basin. We are headwaters for the Colorado River, and a pretty critical one. Geographically, we make up 0.6% of the land area of the Colorado River. But in terms of water we contribute, it's the full 6% of the flows of the Colorado River annually on average. And that doesn't even account for the water that gets pumped up and over the Continental Divide to the Front Range to help water supplies there. So even though we're a pretty small basin, we do have an outsized impact. And our hope is that this project will be both locally and regionally important, something where we really can kind of get dual use out of this data, maybe even triple use for other folks who are researching climate impacts on mountain systems. So what are we studying? What are we collecting to get that information? To kind of orient you, this station is a typical instrumentation suite for what you would see at one of our stations. Starting from the top, we have a tipping bucket rain gauge. Just below that is a solar panel to give us power for the whole station. Next to that, you see the radiation shield that protects our temperature and relative humidity sensor. And then below that is our logger box. This is a cellular capable logger box. So it's collecting data every 20 minutes, sending it out about every 4 hours, which is pretty great. And this is the equipment we use for most of our stations, or the onset logger boxes. For stations that don't have cellular capability, where we've had to go with a satellite box, we have had some other companies' equipment out there. Then under the ground at 2, 8, and 20-inch depths, we have soil moisture sensors. So that's 5, 20, and 50 centimeters. And then 8 inches down, we have a soil temperature probe. And for soil moisture at this site, we are using the Decagon dielectric probes. All of the sites use the Decagon dielectric smart sensors, except for our newest site at Castle Creek, which is a mix of Campbell and Stevens equipment. And so the soil moisture sensors at that one are Stevens hydroprobes. So what are we hoping to do with this data once we collect it? Is always a good question to ask. We have both long-term and near-term goals for the network. For the long-term, oh, there's a hummingbird, how exciting. We're looking for climate changes over time. So we're hoping that we will eventually have a multi-decadal record where we can really start to see, as we're seeing warming temperatures, which is something that's already happening up here, what does that mean for soil moisture and for water supply and for the plants that are relying on that. In the near term, we have some questions we're able to answer and talk to about with our local funders. And that's actually really important to us, because if we're asking for funding for maintaining these stations for the long term, it's helpful for them to be able to go back to whoever they're accountable to and say, here's what we've learned so far. And so in terms of that, we're looking a lot at kind of just system dynamics or interplay between different variables. So another example of the type of data that we found useful in the near term is just year-to-year comparisons. So we just had a very large rain event here a couple weeks ago, but prior to that, this was an extremely dry summer in the Roaring Fork Valley. Throughout April and May, we had almost no rain, and there was a huge concern about fire and about water supplies. And so I had partners asking me, how does this year compare to 2018, which was another year when we had a really large fire up here, and it was a year that was on everyone's mind. And so what I could tell them was, these are the types of things that we can look at that are similar or different from 2018. So here, this graph right here is one that I actually used directly with partners, where I could show them things like date of snowmelt, which ties into, of course, date of soil saturation and how early we see soil drying in the spring and summer. I could also point out things aside from rainfall, such as the importance of drought memory from year to year. So going into 2018 versus going into this year, what was the soil moisture level for fall? So what was our start point for taking up water in the spring when the snow melted? And that's something that was a message that really got home to folks this year, because our streams and rivers were only at about 40 to 60% of average flows this summer, whereas our snowpack had been around 80%. And so there was this question about, where does that gap come from? And so this was a really nice visual way where they could easily see the soil moisture component of that question. So that's where we're at right now. Those are the types of things we're currently looking at. And looking forward, we have big ambitions for this network. So this station here is officially turning 10 years old. And as we look forward to the next 10 years of this network, we want to start thinking about what should that look like in a really strategic way. So as we move forward with this project, There are a couple challenges that I'm sure will be familiar to a lot of you. One of them is obviously funding, but the other major one is that we're a fairly small organization carrying out a research network. And so this is what makes partnerships really critical to us, whether it's talking about data use and application, or whether we're trying to work on data validation and making sure we're using best practices. We really want to make sure we're working within a community so that we can leverage those different opportunities that different places have. So I'll be putting my contact information at the end of this presentation. Definitely please reach out to me if you're interested in working with us, or if you know anything about best practices for fieldwork and data validation for soil moisture. So the closing thought that I always have out in the field is that behind the data collection and all the other goals we have for this project is this overarching goal that through better understanding these ecosystems that sustain us, these water systems that we rely on, that we can hopefully work with our partners and our stakeholders and the public to make sure that we are able to manage these systems in a way that is sustainable and that is informed. Thank you for your time.
Thank you, Elise, and really enjoyed that presentation. I would say, do we have any questions? I see that you've already put a link to a paper in the chat, and your contact information can go there as well. For your, when you had the camera, you zoomed down when you said you had sensors in the ground, and you zoomed down right at the base. Where are the sensors in relation to the station? We're talking about shadow, range shadows and things like that. You're on mute, by the way.
Thank you. The sensors are fairly close to the station, I'd say within probably a couple feet, but are positioned in such a way that the rain bucket should be emptying pretty much on the other side of the station. And it's not, I don't think there should be too much rain shadow in relation to the station itself, because it's a fairly tight setup at that site. At the one site where we do have a much larger tower, the sensors are positioned further away from the tower, so that they're out from underneath any of the equipment.
And for power, you're running off a solar panel. What size? Very personal question.
The little ones are 6-volt. Our other station, gosh, I don't know off the top of my head, I should, but required a larger solar panel. And in fact, there's one station where we have radiative balance as well as the other basic suite. And that one we did have to put 2 solar panels and 2 separate batteries and logger boxes up there.
Okay, I'll run at least a 10 watt in the forest, and sometimes that's not even enough. Your cover didn't seem to be, it didn't have a high fractional cover. Those look pretty small.
I think that the battery use is fairly low, that even in winter when we do get a fair amount of cloud cover, our batteries seem to hang in there pretty well. And I will say, being in Colorado, we don't have very many cloudy days. So I think even with a smaller solar panel, they're pretty much able to charge almost the entire time, because we just rarely have a day where we'd have 24 hours of cloud cover.
Okay. And before I start asking other questions, any other questions in the crowd? I will ask mine then. Ed Ayers, who speaks later, would maybe ask a similar question. Falling limbs and branches and leaves, do they impact your bucket?
Yeah, so we've had a tree fall on our stations in various capacities a couple different times. It's the aspen groves typically, that the aspens, just being a little bit softer, aren't the sturdiest of trees. And we've just gotten really lucky that it took a couple rain events before we realized our rain bucket had been knocked off and we were able to get out there, but we didn't really have much other station damage aside from that. And then the leaves actually don't seem to be too much of an issue with the rain buckets. They've got that little mesh on top to catch things. The bigger issue, which I discovered just this summer, is actually just like dust and smaller particulate matter getting in there and clogging the funnel of the tipping bucket rain gauge. But that's true at our sites that are very much in open areas, just as much as at our sites that are forested.
Okay, these are all the challenges that the Forest Service will be seeing as they try and deploy. Neon sees them now, because many of their stations are inside the forest canopy, and they have a big challenge with measuring fall through and then separating the leaves and stems and every little thing that jams up their bucket. So very interesting, and I really appreciated the presentation style. So that's a challenge, gauntlet thrown for everyone else to step up their game. We will move on to our next presentation by a duo of Megan Shargorowski and Charlie O'Connell. And let me try and get, Megan, are you doing that live or am I playing it?
It's in the presentation.
Okay, I'll just share and play them.
Good afternoon, everyone, and thanks for being here. My name is Megan Shargorowski, and I'm serving as the director of the Kentucky Climate Center and Kentucky Mesonet at Western Kentucky University. Presenting with me is Charlie O'Connell, who is a Kentucky Mesonet Systems meteorologist and is serving as the project manager for the micronet that we are presenting on today. Over the past few years, we have had numerous discussions with the U.S. Forest Service Office of Sustainability and Climate. This culminated in the creation of a Memorandum of Agreement between the U.S. Forest Service, OSC, and Western Kentucky University, with the goal
I apologize, I'm gonna start that over. I just had a glitch.
Good afternoon, everyone, and thanks for being here. My name is Megan Shargorowski, and I'm serving as the director of the Kentucky Climate Center and Kentucky Mesonet at Western Kentucky University. Presenting with me is Charlie O'Connell, who is a Kentucky Mesonet Systems meteorologist and is serving as the project manager for the micronet that we are presenting on today. Over the past few years, we have had numerous discussions with the U.S. Forest Service Office of Sustainability and Climate. This culminated in the creation of a Memorandum of Agreement between the U.S. Forest Service, OSC, and Western Kentucky University, with the goal of increasing environmental and soil monitoring in the Daniel Boone National Forest in eastern Kentucky. Additional conversations with NIDIS about the interest of drought early warning in Appalachia provided the opportunity to further develop a pilot project in coordination with the National Coordinated Soil Moisture Monitoring Network Initiative. This project will aid in the development of best practices for forest soil monitoring, as well as the collection and measurement of geospatial metadata. The photo here is of one of the existing Kentucky Mesonet stations in the Daniel Boone National Forest in the Stearns Ranger District near the Kentucky-Tennessee border.
The Daniel Boone National Forest Soil Moisture Micronet will be a spatially dense network of soil moisture monitoring stations, with the aim to understand the sensitivity of different drivers of drought as well as drought impacts, as well to understand the response to a changing climate. The stations will be located on different topographic features to gain a better understanding of the larger Daniel Boone National Forest and Cumberland Plateau. This micronet will utilize the existing Kentucky Mesonet monitoring network, as well as the Daniel Boone National Forest local expertise. The Kentucky Mesonet currently has 76 stations collecting data every 5 minutes across the state of Kentucky. The current number of stations in the forest is 2, and the forest incorporates 19 Kentucky counties. There is still a lot to figure out for this project. This includes standards, exact locations of the micronet stations, as well as installation procedures. 2 locations have been chosen for scientific and logistical reasons. One location will be in the Cumberland Ranger District to the north, with the second being in the Redbird Ranger District to the east. One of these locations will be co-located with a Kentucky Mesonet station. This station will be located at the Frenchburg Job Corps Civilian Conservation Center. The micronet will utilize transects on different topographic features and aspects, incorporating various microfeatures and elevations. Remote monitoring will occur. This will utilize cell and radio communications, and this will send data back to a live web page. In the Cumberland Ranger District, we are considering using the Edwards branch, represented here by the line in the northeast to southwest direction. It ranges in elevation from 650 to 1,250 feet and is approximately 2 miles long. In the northeast area of the branch is the Frenchburg Job Corps Civilian Conservation Center, where we propose locating a Kentucky Mesonet station. This drainage would allow us to capture different topographic features that represent the larger area. For the Redbird Ranger District micronet, we are considering locating it adjacent to the Peabody Weather Station, utilizing the hill slopes around it. These hill slopes range from 850 to 1,450 feet, with a road leading up to the weather station. The monitoring concept here would be exactly.
Once you have collected all of this environmental and soil data, it's critical to put it into context with metadata. While basic metadata practices, such as latitude and longitude or serial numbers, are fairly commonplace, we wanted to push those boundaries with this project by adding layers of geospatial data that help categorize data points. In complex terrain, spatial metadata can provide critical insights to aid interpretation of near-surface environmental data. We have put together an advisory committee of experts from across the U.S. to help us create a functional requirements document for the development of a geospatial metadata database. While this is initially being tailored for Kentucky Mesonet stations and the Daniel Boone National Forest soil monitoring micronet, the expectation is for this database to be flexible enough to use with any network. When considering the functional requirements, we want to consider who would use this, what metadata should be used, how would it specifically be used by industry experts, such as soil scientists and water resource managers. The next phase of the project will take these functional requirements to create a pilot database and interface. We will seek out focus group testers, most likely from the advisory committee, but perhaps beyond, to further examine the feasibility of the measurement or collection and the usability of the interface. Let's take a closer look at a couple of metadata categories to be included in the geospatial metadata database. Here you can see an NRCS soil map and a PDON description for a Kentucky Mesonet station located in western Kentucky. These detail some of the characteristics of the soil near the station, as well as the profile at the station where the soil probes are located. Additional soil analysis and field observations can further characterize the soil. Derived values such as field capacity and wilting point can be determined from existing soil profile data, but can also be measured. The Kentucky Mesonet has introduced a suite of spatial metadata products as an aid to professionals for interpreting micrometeorological influences on observations from our stations. This suite is produced from digital elevation models utilizing 1/3 arcsecond data and land cover classifications derived from Landsat imagery and geospatial ancillary datasets. A customized application of a geographic information system creates the images and is further automated by a Python script written by a former undergraduate student who worked on our team. While these are currently based on Kentucky Mesonet station locations, the process can easily be replicated for any desired location. It includes the following maps: elevation above mean sea level and relative to the station, land use, topographic hill shading, slope, and aspect. Each map is generated for a buffered area defined by a 5-kilometer radius centered on a Kentucky Mesonet station and is produced as a raster image at a resolution of about 10 meters. We also have these images generated for a 1-kilometer buffer as well, which proves to be very useful when looking closer at the complex terrain in eastern Kentucky. Please keep in mind that the geoprofiles and soil metadata are only a portion of the larger geospatial metadata repository. Once established, it will provide an opportunity for researchers and other users to filter stations and sensors to fit specific criteria needed for their datasets.
Thank you all for listening to our presentation, where we have discussed the Daniel Boone National Forest Micronet, as well as the Geospatial Metadata Database. Any questions or feedback would be much appreciated.
Thank you, Megan and Charlie. And I think at least Megan is in the chat. Yep, there you are. Do we have any questions? I can start. How is the?
Yes, I'm here.
A little choppy. So how is the network is funded? What's the prognosis for the network coming to the future, and how is it funded?
The initial funding is through NIDIS, and we have a couple different phases that we expect to hit. This initial
You're breaking up a little bit. So
setup is fully funded off of that. The Kentucky Mesonet will be absorbing the future maintenance. The Daniel Boone National Forest, we are working with some local partners, as it is quite a trek from Bowling Green.
yeah, that'd be easier. And I think Tyson might have a question. He can move to the. If you want to ask now, Tyson, she can answer in the chat, or ask in the chat.
I'll put my question in the chat.
Okay. Yeah, that happens. I actually had a tornado warning here, which threw me off for a little bit. I was a little worried, or a watch. I guess it was just a watch. The subtleties are lost on me. So we will move on to the next and final presentation for today by Ed Ayers. And let me just get it set up. So Ed is works with the NEON, the National Ecological Observing Network, working for Patel Ecology. And here you go, Ed.
Hi, I'm Ed Ayers. I'll be presenting results from a project that my colleagues and I recently finished, validating SMAP soil moisture at forested and unforested NEON sites. This was a really collaborative project, and I've listed all of the co-authors here, as well as others who contributed to the project. So soil moisture is, of course, really important for forest health. So there's this need for regional to global scale soil moisture data from forests. But SMAP, with SMAP being one of the major soil moisture data providers, the SMAP soil moisture data for forests is all flagged as potentially unreliable due to interference from the water content of the plant canopy interfering with the satellite's measurements. In addition to that, forests have also been very underrepresented in previous SMAP validation campaigns. In the most recent campaign, they only accounted for about 1% of sites, despite the fact that forests occupy about 20 to 30% of the land surface. So we really don't know how well SMAP is performing in forests. This is the data that we used for this. For SMAP, it was 0 to 5 centimeters soil moisture with a temporal resolution of 2 to 3 days, a spatial resolution of about 1,000 square kilometers, and close to global coverage. For NEON, we used the shallowest sensor, sensors that's about 6 centimeters deep, the 30-minute averaging interval with a spatial resolution of around 0.1, square kilometers, and that's because it comes from 5 soil plots spaced up to about 50 meters apart. And this is generated from 47 sites dotted around the US, representing a really wide range of ecosystems and soil types. And on the lower left picture here, you can see in the white areas, the areas that are typically flagged by SMAP. And you can see that those white areas really closely match forest distributions globally. So just emphasizing how much of the forested soil moisture data is flagged by SMAP. I won't spend much time on this slide, but I did want to mention, given the huge differences in the NEON versus SMAP spatial scales, we wanted to check that the environments that they were measuring were broadly similar. And the upshot of this was that despite these huge differences in scale, the NEON and SMAP measurements did seem to reflect similar environments. So making these comparisons did seem to be fair. Once we combined the data, we had over 12,000 measurements from 40 different sites, 21 unforested sites, 19 forested sites, and collectively this represented 88 site years of data. On the right here, I've shown the data for one of our sites with the NEON data in red, the SMAP data in black. And once we produced these correlations, we calculated 6 different correlation parameters: the root mean squared deviation, the unbiased root mean squared deviation, which I've highlighted because that's the primary metric that SMAP uses to quantify performance. And that you can think of that as representing the sensitivity of SMAP to changes in soil moisture. The mean difference, which includes measurement bias as well as representativeness errors, the absolute mean difference, the Pearson correlation statistic, and the slope of the correlation. So first, looking at the unforested sites, we found that SMAP was sensitive to changes in soil moisture. The unbiased root mean squared deviation was 0.05 meters cubed per meters cubed. So no real surprise here. There have been a ton of previous validation studies of SMAP at unforested sites. But what was encouraging to see was that the results from the NEON validation were very similar to previous sparse networks validations. So that gives us some confidence that NEON is performing at least as reliably as those other sparse networks, and gives us some confidence when we move on to looking at the forested sites where there haven't been very many previous validations at all. So looking at those forested sites, we found that the correlations were consistently weaker, but that the SMAP data still contained useful information. So the unbiased root mean squared deviation was around 0.06 meters cubed per meters cubed. So indicating that you can identify temporal trends in soil moisture in forests, at least when you're aggregating across sites. In contrast, the absolute values were really not very reliable. The root mean squared deviation was 0.15 meters cubed per meters cubed. Some of that is due to representativeness errors, so certainly adding some more widely distributed sensors to the validation sites could help, but also a large proportion of it likely comes from SMAP measurement biases as well. And on the bottom here, I've just plotted histograms of some of these correlation parameters for the forested sites in orange and the non-forested sites in blue. And again, you can see that these correlations in forests were generally weaker, but not terrible. So since we know that SMAP is sensitive to vegetation water content, we looked for other NEON data products that we would expect to closely relate to that. And we identified 3 different data products: above ground biomass, NDII, which is a remotely sensed index of vegetation water content, and canopy height. And if we first look at these in relation to unbiased root mean squared deviation, which is the top row in this figure, you can see that all 3 showed a positive correlation with the unbiased root mean squared deviation. So that's kind of indicating that no matter how good SMAP gets at minimizing measurement biases, we're never going to see the same sensitivity to changes in soil moisture in forests that we do in unforested sites. But it doesn't increase to such a high value that it becomes kind of useless. So even at the high end for these densest, wettest canopies and tallest canopies, we're still seeing unbiased root mean squared deviations of 0.07 meters cubed per meters cubed. So perhaps not as sensitive as we would like, but not terrible either. Even more encouraging when we looked at relationships with mean difference, which is, as I mentioned, includes SMAP measurement bias and also root mean squared deviation. We found that 2 of these ecosystem properties were correlated with this. So you can see that was for NDII and canopy height. And that's kind of indicating that these SMAP algorithms may not be parameterized optimally for forests, perhaps also not surprising since SMAP was primarily focused on unforested sites, but it also indicates that these algorithms could be reparameterized and, to improve the performance by taking into account these ecosystem properties. Another thing we did was look at the sites with particularly poor correlations, which we defined as having an R of less than 0.3. There were 5 sites in this category, all of which were forested sites. And when we looked into what was going on here, we found that there were 2 causes. So for 3 of the sites, we saw clear signals of the SMAP data just saturating at very high water contents. And you can see this on the lower left time series, where the neon data in red and the SMAP data in black. And you can see that the SMAP data is just flatlining at these very high soil moistures for almost the entire growing season. So again, that's kind of indicating that the SMAP algorithms are not well parameterized for these sites and perhaps forested sites generally. The other issue that we saw, which we saw at 2 sites, was particularly large variation in soil moisture among the different neon soil plots. And so that either could indicate data quality issues, perhaps one of the sensors wasn't working properly or had a poor installation, or perhaps just there's particularly high spatial variability at those sites. But again, there's something that we could do to improve that. So of course, ensuring that our in situ measurements are as accurate as possible, trying to replace malfunctioning sensors in a timely manner, or redoing installations if necessary, or possibly even removing locations if we consider them not representative of a spatial scale of interest, although I kind of hesitate to do the latter one. So in conclusion, SMAP can reliably detect changes in forest soil moisture, at least when aggregating across widely distributed sites. If you're looking at an individual SMAP footprint, you definitely want to take a little more caution when you look at those trends, because in some cases, those correlations were quite good, and in other cases, they were quite bad. In contrast, the absolute SMAP soil moistures are often not representative for forests, but there is some indication that reparameterizing the SMAP algorithms for forests could help by accounting for canopy height and vegetation water content. And encouragingly, there are already remotely sensed data that exist for both of these ecosystem properties globally. And as with any validation study, representativeness errors remain. So certainly adding some more widely distributed soil moisture monitoring locations to the forested validation sites would help, as would adding more forested core and sparse validation sites generally, especially for particularly underrepresented forest types like tropical forests. And I put at the bottom here the link to our preprint that describes all of these results and is currently under review. Thank you.
Thank you, Ed. And Ed is here, and we have a question in the chat from Saab. Does forest canopy change seasonally? Does unbiased RMSD of 0.06 depend on whether it's evergreen or deciduous cover? Did we split across evergreen or deciduous?
Yeah, we tried to look at that to some extent, and it was certainly there are changes in the forest canopy seasonally, especially of course for the deciduous dominated forests. We tried to look at whether the unbiased root mean squared deviation and the other correlation parameters varied seasonally.
The last presentation.
Oh, okay. And
should be over shortly.
Okay. And we didn't see much of a sign of that. But it was complicated by the fact that we often have snowpack at many of the sites, and the SMAP signal can't be measured through they can't measure soil moisture through the snowpack. So that cut out a decent number of sites. And also when there were freezing temperatures, the neon couldn't measure soil moisture either at those sites. So it wasn't a perfect comparison, but we didn't see obvious signs of the unbiased root mean squared deviation or other correlation parameters varying between evergreen and deciduous sites seasonally. But it kind of makes sense that it might, though.
Okay. Other questions in the chat or live? Tyson?
Hey, yeah, thanks, Ed. Really interesting talk, and this whole section on the forest is really interesting. I'm curious about metrics like the Nash Sutcliffe efficiency for these sites, if we compare the SMAP versus the in situ in the forest, do they tend to have positive Nash Sutcliffe efficiencies or negative? Or another way to ask it would be the correlation coefficients, are they statistically significant? So some of those kind of questions I wonder about.
Are those correlations statistically significant? I guess we didn't, for like individual sites. Yeah, we didn't investigate, I guess, on an individual site basis whether each correlation was statistically significant. I mean, I've got to assume that sometimes, especially for places where the SMAP signal just flatlines, it's hard to imagine that that would be statistically significant. We did all of our analysis on the sort of aggregation of all of the correlations. And in those cases, the relationships, at least that we were seeing with the ecosystem properties were, well, were statistically significant, at least when I indicated that there was a regression line on the plots.
I think it comes back as correlated and significantly correlated challenges if it's practically correlated, how significant, or is this temperature effects and things like that. I know Andreas couldn't be here this week, but he's working on an algorithm he's refining the forest algorithm for SMAP to account for the differences in the assumptions made about vegetation optical depth. So it's not designed to be able to cover forests, and there has to be a lot of it can't be one algorithm can't cover all scenarios at the Earth's surface. So there needs to be some adjustments, and they're working on that. But visually, you can see some trends, and they look real. They would probably pass most tests, but is it practically? The value of it is still to be determined, the magnitude of the value. So question from Jun Wang. For SMAP validation, does soil moisture percentage work better than soil moisture water content? I think I can answer I'm not positive what you mean by percentile, and Andreas would answer this better. But usually the comparison points are in a unbiased RMSD or RMSE if we know the true value. For the purposes of SMAP, that's how most of the data is compared to in situ data. Ed, do you have anything to add to that?
No, not really. I mean, I kind of feel like that would be what you're getting from the unbiased root mean squared deviation information.
Brianna asked, do you think there's potential value in using soil moisture anomalies rather than the volumetric water content for some applications in forest areas? Your results seem to suggest this may be a better approach. So from a forester perspective.
Yeah, I think that our findings do indicate that that would generally be or give you better results. You can see these temporal trends, at least when aggregating across a number of sites, whereas when you look at these absolute values, that definitely is a lot weaker relationships. At least I hope I understood the question correctly there.
From Devendra, looks like SMAP may do better in thinned forest areas than enclosed canopy forests. That really comes from the fact that the challenge of SMAP is to see through vegetation, not optically like you think, but because it influences there's water in those trees and those leaves. So a thinned forest has less water, and it's the water that interferes with the signal, because it is really observing it's observing a brightness temperature, which is related to the water content in its look. So trying to see through water to see more water is where the challenge is. And usually there's a threshold of 5 kilograms per square meter of water that they don't say they can see through, and we're trying to stretch the limit up to a forest canopy. Thinner forests are going to be easier, and you're probably going to see it's less influence from the forest components. So yes, thin forests are easier. We're trying to determine at what point at how large of a forest or thick of a forest is just too much to see and influence. And then Fred, did you identify footprint land cover uniformity effects? And
maybe if you go back to the previous slide, that has some information about that. So in this case, we looked at a few different ecosystem properties, so vegetation, water content, index, and canopy height from the NEON remote sensing data. We compared it for a relatively small area around the NEON site, 1 square kilometer, which is on the x-axis for all of these plots, and then to a larger area. So for the top 2 plots, it's 190 square kilometers. And generally, we saw quite decent correlations here. So in most cases, these sites seemed relatively uniform, at least, between these 2 spatial scales. And we also saw that when we went all the way up to the SMAP footprint scale using Landsat data, and that's the bottom plot here. So with around 1,000 square kilometer scale. So I guess we've got some indication that it is at those 2 different scales, but we didn't look at all of the intervening scales. And one more thing, I guess, is the dominant land cover occupied quite a large area of each SMAP footprint at the sites that contain, or the footprints that contain the NEON sites, so about 70% of the footprint. So indicating that they're relatively homogeneous.
Okay. Thanks. Other questions? Devendra? Okay. We are at 4:47. That is certainly enough reasonable time to end for the day with the science part. Any other comments from the crowd or the co-organizers?